If I do a controller on this blue one here, it means that I do an MPC that is, for example, based on the linearized system. The controller, will it determine U, delta U, or you do not know? If I make an MPC, I do have a system. I find an equilibrium. I linearize. After the linearization, as we will see, I design the controller based on the linearization. Will the controller spit out U or delta U? What would you say, people? What would you say? What would you say? Is going to spit out this one, delta U. If some controllers will basically be, let's make some state space allocation. So we are going to have basically U equals to Kx, x and y, assuming it's the same thingy. If I'm working with the linearized system, I'm going to have that actually this one is going to be delta x, this is going to be delta U. Okay? Together, if the equations are of the linearized system is delta stuff, it will produce delta U. Why am I mentioning this one? Think at the problem of having a crane with a magnetic lifter, okay, that is trying to make something here fly, okay? And the magnetic force that this one shall exert on this piece should kind of be equal to the weight of the stuff. So it has to generate a force, uplifting force, let's say of 100 kilos. Okay? And then this means that somehow I might have an equilibrium around 100 kilos of my U has to produce 100 kilos, and this is my equilibrium. And then I might have a controller that might want to do some levitation stuff. And the controller will produce a delta U that might be a little bit more or less in time than 0, because somehow you want to make this one levitate. Okay? Together? So you got the equilibrium, and then you will have a deviation from the equilibrium, and the controller will try to compensate the deviation from the equilibrium. True? If you tell the micro, inject into the actual actuators this value here, what happens? You are missing the 100 kilos. That is the baseline that you should give. You see it? You see? Simon Hoff. How many know Simon Hoff? One of my PhD students. Nobody. Almost lost a finger with a blue rod. Because they put the controller inside and the stuff started spinning, and there was a problem with the baseline of the equilibrium. They forgot to put basically the baseline of the equilibrium in the U's. The U's were kind of not working properly. The rod started rotating while he was having that. problem was forgot to put U equilibrium back. And they put only delta U in the controller. Or better, not in the controller, in the actuators, in the motors. Okay? Do you see the point, people? You see the point? Hmm? Because very often in this course, we are going to work with the linearized system. Whenever we work with the linearized system, we kind of assume that we are working with the system, but it's not. There's an offset that very often people forget, that we shall not forget. Do you see it, people? This is on Y, but imagine that we were also having a U and we were working here. We would have an offset U equilibrium, okay, to inject. Together? Question.
So I got what you're saying, but the only reason that comes to my mind when if I have to justify why it's convenient to linearizing the equilibrium point is in order to have in the new coordinate system a linear function, because otherwise it's not linear.
So we have the original, and we have here something that doesn't look a plane. True? This is an equilibrium. I want to think, okay, if my disturbance brings me here, I will have a trajectory. True? Will this trajectory be a complex exponential? No, because this stuff here is not a plane. Okay, so I need Euler to generate that trajectory. And if I want to do MPC, it's going to take a lot of time. What can I do? I can linearize this stuff here and say, okay, we are sufficiently close that the linearization is meaningful. I can generate an approximate trajectory that is a complex exponential very fast. And I can put it inside here. But whenever I put inside here, maybe I will have some controller designed on it. The controller shall remember that you have, I don't know, 100 newtons as a baseline to throw, not only a deviation, because the controller will work here. True? The controller will work here on this axis. I draw it in a different way, on this axis. True? And the coordinate will be delta U. In time, you will get something that does like this, and this is 0 in the axis delta U time. But you have to put something that is U of time. So you have to put in the actuators this stuff here. You got the point? That is what goes inside the motors. Okay? If you forget that stuff, you get you got an engine that is going to be doing very differently than what you would like to have. You get the point? True? Perfect.
Is it because we tend to work more in like it's more relevant to be around an equilibrium point?
If we do not linearize around an equilibrium point, we get an affine system for which things are slightly different. So if we work around an equilibrium point, mathematics is simpler. And very typically, with production plants, you do not want your nuclear power plant to go up and back and forth all the time. So you want it to be stable around a certain nominal point. That is going to be an equilibrium, and you would like it to be also asymptotically stable, by the way, especially with a nuclear power plant. You don't want it to be unstable. True? But this is not true in general. Because, for example, for robotics, you will have movements. You will have other types of controllers, more complex, of course. This course here, we do the basics, people. We cannot do we cannot do feedback linearization now or sliding mode control. We do LQR. Perfect. So, do we linearize here? Yes, no, I don't know. Discuss. Always discuss. Because do not wait for me to say discuss. Do not wait for me to say discuss. Always chat. People, what would you say? What would you say, people? Here, there's no equilibrium. Perfect. Hmm? A system without equilibrium. Is it meaningful to linearize here? Yes, no, I do not know. So, people, what would you say? I see people still talking. Okay. People, here, do we have the derivative that is well defined here? No, we can't compute the derivative here. Okay, so perfect. How much are we together, people, up to now? Very much, not at all, kind of. Okay. And an example that I already did last time. If I take these as an equilibrium here, what do I get as a linearization? I get something that is going to be very different, true? Do you remember that I was saying before something that was very essential? Whenever we consider initial conditions that belong to the basin of attraction of that equilibrium, and if that equilibrium is asymptotically stable, then we have a good situation. What is the basin of attraction of an equilibrium? If I start here, do I go eventually here? Definitely not. True? If I start here, I will escape. If I start here, will I go end up on this equilibrium? Definitely not. True? What is the subset of the phase portrait, of the phase space, for which, starting from that subset, eventually we converge to that specific equilibrium? This one. Those points here are the basin of attraction of this stuff here. Shall I do a little bit bigger? You got the point, true? So here, linearization, it's actually meaningful and becomes better and better and better, but only if we start with the basin of attraction. Okay. Okay. This one, if we start in a basin of attraction. Let's go to some question. Okay, let's see. Go. Discuss and go. Do you need more time? Do you need more time? Are you taking me? Okay, so what would you say? What would you say? Why? Because this one, for every equilibrium point, we will have our own, how do you say, linearization. True? For this one, yeah, we know that from a practical perspective, we will have less trust in the linearization in the sense that it will be meaningful only for few points. True? This one, the operation of linearization is made on purpose for linearizing, so maybe it's going to be similar to this one, but it's meaningful. In this case, has no sense. Together, people, perfect. Let's take 11 minutes of pause. Let's start at 15:15.